Okay, this is it for Chapter 6. This is Chapter 6. This is going to be Chapter 6, I guess, Part 3. And we're going to cover 4 different sections today, 6.6 through 6.9. We're going to talk about the shapes of orbitals real quickly. We're going to talk about electron spin, and then we're going to get to the meat of the section, which is about electron configuration and orbital diagrams. Okay, if we remember from what we've talked about, each shell, or a lot of times what we call each orbit, and each subshell or each suborbit within each atom all have a different amount of energy associated with them. So you've got the main orbit, which is the third principal quantum number, and then within that third principal quantum number, you've got the suborbits or the subshells, which are the 3s, the 3p, and the 3d. And they all have a different energy associated with them. Remember that the closer, if this is the nucleus here, the closer you are to the nucleus, the lower the energy. The farther you go out, the higher the energy in the atom. So the higher the energy. Okay, and then what we're going to see is these different energies affect the shape of these orbitals. And we're also going to see how each electron must have its own set of what are called quantum numbers. Okay, so as we talked about, each orbital within each orbit has an energy associated with it. But it also gives us an idea about where those electrons are. We know that the electrons spin around the nucleus in different ways and directions depending on which way it's found, and in which orbit it's found, excuse me. And so what we do, if we remember back to our solar system model, the way that we represent orbitals is we draw what's called a boundary surface. That's often also called a node. And what that boundary surface is it shows where the electron cannot be found. So it's kind of like a border between electrons and electrons. For example, if you have an s orbital, the s orbital means right here is the nucleus. And that means, again, when we draw electrons, many times we put them right here. And we say the 1s has 2 electrons in it. But that is actually completely and totally incorrect. What that circle means is that the 2 electrons that are in this 1s orbital can be found anywhere from here out to here. But they cannot be found right on that line. So you might have an electron here and an electron here. This whole blue area is what we refer to as the electron density, where that is the most likely spot to find those 2 electrons. So when we do that, we can put those 2 there. It's almost as if you took a picture of an atom 1 billion times, and each time you took it, it showed the 2 electrons. You would never ever find an electron right here. You would find those 2 electrons somewhere in this area, but you'd never find them all the way out here. And notice that the s orbitals are round. They are circular in shape, and as you go to higher energy levels or higher orbits, they get bigger. It's kind of like this is the Mercury orbit, and this is the Venus, this is the Earth, and all of those orbits are bigger than the previous one. The p orbitals are a little bit different, where remember that with the p, you can have 3 different p orbitals, where you've got a p orbital that's coming up and coming down, kind of like a dumbbell. And again, you can have 1 electron somewhere in here and 1 electron somewhere in here. And then you have another one that's kind of going sideways to the right and sideways to the left, sticking out from the screen, and then sideways to the left, sticking into the screen, and then sticking out from the screen. And again, these lines out here represent the nodes where there's no probability of finding an electron. The electrons are somewhere in this region. The D's and the F's, don't worry too much about them. That's what the D's look like. Anywhere you can find those electrons in any 4 of those clover leaf-shaped areas. Now, all of the orbitals we've discussed up until now have related to 1 electron in the hydrogen atom. But we can also extend this to many atoms. And this is the important part. In a many electron atom, for any given value of n, remember, which is the principal quantum number, the energy of an orbital increases with an increasing value of L. So as we can see, we've got the 1s and then we've got the 2s. So as you go from 1 to 2, the energy increases. But then as you go from s to p, the energy also increases. So as you go from s to p, the energy, you're going from L equals 0 to L equals 1. And as you go up from s to p, you're also increasing in energy. Okay, And so our last principle, our last quantum number, remember we had n, l, m sub l, and m sub s. These three we've talked about. This one we have not. That last one just tells us the spin. That in each of these orbitals, we've got all these spaces here where we can have one electron spinning in a positive way, one electron spinning in a negative way. Positive, negative, positive, negative. So one electron we write as spinning in a positive direction. We write it as positive 1/2, and the other one we write as negative 1/2. Okay, so ms, which is the fourth quantum number, describes the electron spin and has a positive spin or a negative spin. The actual value of 1/2 is not that important. Okay, and then that leads us to our final principle here, in that the Pauli exclusion principle says no two electrons can have the same set of 4 quantum numbers. Or an easier way to put it is every electron must have a unique set of quantum numbers. And that leads us to the conclusion that an orbital can hold a maximum of 2 electrons, because if we come back to here, we've got one electron spinning this way, one electron spinning this way. So it can only hold 2 electrons. Okay, so what we might see is we might see a question like this. Give all of the permissible sets of 4 quantum numbers for each of the outermost electrons in a single zinc atom when it's in its ground state. What we have to be able to do here is we have to be able to look at the periodic table and see where zinc is. If we look at where zinc is on the periodic table, it's in the 4th period, and it is the 12th element over. And that is the 3D orbital. And we'll talk, let's go ahead and jump. We're going to come back to this here in just a second, and we'll talk about why that's the 3D orbital. And we'll talk about what these numbers all mean here. Okay, the electron configuration is just what it means. It's the configuration. It's how the electrons are configured in an atom. And the easiest way to get to that is just to look at the ground state, or when all of the electrons are in their lowest possible energy state. And the way that you write the electron configuration is you just use the periodic table. Let me see if I have that in here. I do not have that in here. There it is right there. The way that you write an electron configuration is, first of all, helium can be moved over here. So you're going to have this right here. So you're going to have, excuse me, 1. This is also 1s. As you can see, the alkali metals and the alkaline earth metals are all in what's called the s orbital. The borons to neons and all of these ones over here, these are all part of the p orbital. So we've got the s, the p, these are all the d's, and these are all the f's. And again, the easiest way to look at it is every time you write an electron configuration, is you're writing, starting from the nucleus, you're writing where all of those electrons are. So you always start right here with element number 1. So if we were writing the electron configuration for lithium, the way that we would write that is we would say, okay, lithium, how many total electrons? Lithium's right here. How many total electrons does lithium have? Lithium has 3. So lithium it has this electron right here, this electron right here, and this electron right here. So the way that we write that is we write 1s for this whole orbital. And how many electrons are in there? 1, 2. So the way that we say that is we say lithium is 1s2, and then we jump down to here to where lithium is, and then we go 2s1. So every time you write an electron configuration, you always start with hydrogen. And you always start with 1s, and then you go to 2s, and you basically just follow the periodic table. So it goes 1s, 2s, 2p, and you can have up to 1, 2, 3, 4, 5, 6. So if we did, for example, nitrogen, again, starting with hydrogen, would be 1s2, takes you to helium. 2s2 fills up this one right here. And then nitrogen is right here. So we would have to go 2p, 1, 2, 3. So nitrogen is 1s2, 2s2, 2p3. Okay, and you basically just follow along the periodic table, and just by atomic number, you just keep going across. When you get to the end, you go down. So if we were to do a bigger one, such as zinc, which we'll go back to here in just a second, zinc, again, starting with hydrogen, would be 1s2, 2s2, takes us to here. 2p all the way to the end is 6. And then after 2p, we jump down to 3s. So 3s2 takes us to here. And notice the s's always have 2. The p's, when they're full, are always going to have 6. So now we're to here, 3p, 6. And then 4s2. Now here's where you got to be careful. Because after 4s2, notice that it jumps back to 3d. So it's 3d10. Okay? Now, those are the last electrons in our zinc atom, is at the 3d10. So taking that into account, if we come all the way back here to that original question, right here, remember that I said that zinc, if they're talking about the quantum numbers for each of the outermost electrons. Okay, a lot of times we call those valence electrons. The valence electrons are the outermost electrons. And those electrons are in the 3d orbital. So 3d, when they say the 4 quantum numbers, that means n, l, m sub l, and m sub s. So a set of possible quantum numbers is n, remember, is this number right here. So n is always 3. L is, remember that when L equals 0, 1, 2, or 3, the letter that you use is S, P, D, or F. Notice that we're in the 3D orbital. So when L equals 2, then you're in the D. So when it's D, the L must equal 2. If it was 3p, then L would have to equal 1. If it was 3s, it'd have to equal 0. Okay, and then m sub L, so all of them. Notice that all of them have 3 and all of them have 2. 3, 2. M sub L, however, has that all of the numbers from positive L to negative L. So it's every number from positive L to negative L. And we do that twice because half of the electrons spin positively, half of the electrons spin negatively. So on the exam, what they might do is they might give you a question where they might say, you know, a multiple choice question where they might say, which of the following could be the 4 quantum numbers for zinc? And they'll have one of these choices and then 4 wrong ones. And you would have to identify this one, and then it had to be, this number would have to be a number between -2 and +2, and then this one would either have to be a positive or a -1/2. And it wouldn't, either one wouldn't matter. Okay, so let's look. Here's lithium again. From the periodic table, we know lithium has 3 electrons. We know each orbital can only hold 2. And the s orbit has 1 orbital. So it can only hold 2 electrons. That's why it was 1s2, 2s2, because the s's can only hold 2. The p can hold up to 6, the d can hold up to 10, and the f can hold up to 14 electrons. Okay, so the first energy level, as we saw, is the 1s orbital. And again, that's hydrogen and helium. And so we just start filling them in. So we got the 1s2, 2s1. Okay, another way we can write that is we can write what's called the orbital diagram. So this here is the electron configuration. And the orbital diagram is the same thing, but instead of just writing 1s2, we write the 1s below it, and then we show 1 electron spinning positively, 1 electron spinning negatively. And then for 2s, 1 positively, and then that's it, because there's only 1 electron in the 2s. Okay, so here's some different orbital diagrams from lithium all the way to sodium. Notice here that lithium, 1s2, 2s1. Beryllium would be 1s2, 2s2. Notice here with carbon and nitrogen. Okay, one of the things that's important is for degenerate orbitals, and that means for orbitals that are not filled, The lowest energy is attained when the number of electrons with the same spin is maximized. So what that means is right here, you do not make pairs until you have at least one electron in each one. So for example, the nitrogen is 1s2, and the 2 shouldn't be there because the 2 is right here, 2s2, and this is 2p3. And notice that the p orbit has 3 of those subshells, 3 of the different orbitals in them. So you've got one electron each spinning in the same direction. This is sometimes referred to as the rule of maximum multiplicity, where you have the largest number of electrons you can spinning in the same direction. But basically all that means is you do not make pairs. So the next one would be oxygen. Oxygen would be 1s2, 2s2, 2p4, and the 4 would be this pair right here. And then you've got fluorine. Fluorine would have this one paired, and then neon, our noble gas, would have that one paired. And then we look down at sodium. Sodium's got them all filled, and then sodium's got the 1s2, 2s2, 2p6, and then 3s1. Okay, so they want you to write the electron configuration and orbital diagram for oxygen, which has an atomic number of 8, and then how many unpaired electrons should oxygen have. So our electron configuration would be 1s2, 2s2, 2p4. Using just that information, though, it's hard to tell how many unpaired electrons you would have. And that's where the orbital diagram is very helpful, because once we do the orbital diagram, we can see that oxygen has 2 unpaired electrons. Okay, a lot of times, too, instead of writing out the whole electron configuration, you can write what's called the noble gas or the condensed electron configuration, and that is where you only show the valence electrons. So if you have something like oxygen, where you've got the 1s electrons, the 2s electrons, and the 2p, and I'm just going to write them as circles even though we know they're not circles. The valence electrons are the ones that are in the last energy level, so it's the last s and p. And the easiest way to determine valence electrons is simply looking at the periodic table and just counting. Alkali metals have 1 valence electron. Alkaline earth metals have 2, and then it just goes 3, 4, 5, 6, 7, 8. Except obviously for helium. Helium can't have 2 valence electrons. Can't have 8 valence electrons. It only has 2. So the valence electrons are the electrons in the last s and p orbitals. Everything else that are in the inner shell are called core electrons. Okay, so what we can do is we just start with the noble gas closest to that element. Okay, so for sodium, sodium is number 11. And normally the full electron configuration is 1s2, 2s2, 2p6, 3s1. However, if we go to the noble gas of lower atomic number before it, so the noble gas that comes before sodium is neon. And then basically neon takes up this whole part right there. So that's out, so it's just neon 3s1. And that's it. Lithium, there would be, lithium would just be helium 2s1. Okay, so here again, this is how you fill them. A couple of things about that. After the 6s orbital, you jump down to the f orbit. So here, right here, 6s, and again, if you follow the periodic table by atomic number, that's what happens. If you look at your own periodic table, it goes from 57 or 56 barium down to number 57 lanthanum. So you go 6s2, then it would be 4f. Notice that f's are 2 behind. 4f14, and then you'd come back up to the d's, just like the periodic table goes. Okay, 2 is how many go in an S, 6 in a P, 10 in a D, 14 in an F. 1s, notice that the S's start with 1, the P's start with 2, the D's start with 3, the F's start with 4. That's why if we look here, that's why the D's are 1 behind and the F's are 2 behind, because the first S is 1, the first P is 2, first D is 3, the first F is 4. Okay, a couple of exceptions to that. Sometimes elements have very similar energies, and when one electron can be removed to have it completely filled, it actually makes it much more stable. And the only time that happens is with chromium, molybdenum, and tungsten, and copper, silver, and gold. And what happens is, for example, with, let's look at copper. Copper's number 29, Cu, and it should be argon 4s2 3d9. What actually happens, though, is because that 9 needs one more electron to be filled, one of these electrons gets promoted and it becomes 4s1 3d10. Notice it only happens in that column from copper and silver and gold that have the 3d9, and then the chromium, molybdenum, and tungsten that are, for example, chromium is again argon, this is chromium, would be 4s2 3d4. And so it's got 4s2 3d1 2 3 4. It's got this one blank spot right here. So this electron again gets promoted and comes up to here, and so now it's gone. So the correct way to write chromium is 4s1 3d5. Okay, now with ions, also an exception, when electrons are removed from an atom, so let's say you have Fe3+, when those 3 electrons are removed, they're always removed first from the orbitals with the largest available principal quantum number. So iron 3+, the normal electron configuration for iron would be argon 4s2 3d6. However, with iron 3+, you've lost 3 electrons. So iron 3+, you don't just take 3 electrons away from here, because that is not the largest available principal quantum number. This one is. So it's still argon, but I have to take these 2 away and then take this one away. So it's just argon 3d5. So when you take electrons away, please, and of course they'll always do this with the transition element, because the transition elements, that principal quantum number is lower than this one. So just be aware of that, that when you take electrons away, you take them away from the highest number that's available first. And then you can go to S, P, D, and F and take those ones away. But if you have a 4 and then a 3, those ones go away first, the 4 ones do. So there you go. Okay, and when you add electrons, they go to the lowest available principal quantum number, which makes sense. Okay, so here's tungsten. Tungsten should be 6s2, 4f14, 5d4. However, that one, because the D just needs, again, the 5d, remember, has 5 slots. So it's 1, 2, 3, 4. That one electron, or the one electron from the 6s comes up to here to give us the 6s1, 5d5. Okay, manganese. So that's an example of not an ion, of just those 6 exceptions. Manganese normally is 4s2, 3d5. When it loses 3 electrons, it loses these 2 first, and then one of these to make it just 3d4. Okay, so those are gone. So there are some homework problems. Here's some from your review packet, and I also wanted you to identify 4 possible quantum numbers for each of these 3 elements right here, and we'll talk about it in class.